Greetings everyone. This video is presented by Group 1 for the research paper assignment. We were assigned the research paper on M5 Mastering Page Migration and Memory Management for CXL based tiered memory systems. Our topic was memory management. So coming to the contents, so we will start with introduction, then we will tell about CXL memory and device types, then contributions of the research paper, then some CPU driven solutions, then we will come to CXL driven page migration solutions, then we will get to the main M5, and after that the evaluation and discussion, and at the end we will come to conclusion.
As the data center application demands and the cloud computing services are increasing day by day, there is an increased demand for a higher capacity and a higher bandwidth for our DRAM systems. But if you look at the current DRAM system with its DDR interfaces, which uses parallel transfer of bits from our CPU to our memory, it is scaling up to its limits. There are various limiting constraints, including the pin constraints, because the number of pin counts in our system is confined, and if we try to increase the bandwidth of our DRAM systems with increasing the lanes, there would be a huge number of pins which would be requiring, but that is not allowed in our systems. Also, if we try to increase the speed of transmission of data from a system to a DRAM, since it uses parallel transfer of data, there would be synchronizing and noising issues if we try to increase the frequency of our data transfer up to a certain limit. So, because of these scaling constraints, there exists a solution which is Compute Express Link. The Compute Express Link uses the PCI Express Link and its earlier 5.0 specification as a baseline, and it improves over it. With a fewer pin counts requirement, it does some protocol conversions between the load store instructions to the PCI Express translation layer packets. Because of this, it can be seen as a CXL memory as present in our remote NUMA node, which can be accessed very quickly to our processor. But even though this access is faster, there is an increased latency because of off-chip serial data transmission and subsidiary packets which happen in the CXL architecture. There exist queuing delays for the packets also. Because of this, the entire memory then converts to a tiered memory system. The DDR DRAM being the fast memory and sits on a lower tier, and the CXL DRAM being the slower memory sits on the higher tier. Because of this tiered memory system, we need some page migration solutions in order to migrate our pages from our slow memory to fast memory in order to increase the performance of our programs.
Now, let's move on to the contributions of the research paper. Our research paper highlights three major contributions. First is the development of a CXL driven hot page and hot word profiling solution. The research paper outlines the development of page access counters and word access counter implemented in a FPGA based CXL device. These counters count the number of accesses to every 4 KB page and every 64 byte word in these pages. So these counters exploit the near memory processing capability of the CXL controller to provide a more precise and transparent profiling capability than the previous profiling solutions. Secondly, our research paper highlights that the CPU driven page migration solutions are harmful. The, the pre-existing two CPU driven page migration solutions, ANB and Daemon, often identify warm pages, the pages which are moderately accessed, as compared to hot pages which are more frequently accessed in popular memory intensive applications as hot pages, and tend to migrate them. Also, the pages identified by these CPU driven profiling solutions are often sparse pages, that is only 10 or 20% of the words are accessed in these pages. So and also the performance overhead of migrating these pages are very high, so identifying true hot and dense pages are is very necessary. Thirdly, our research paper tells us about a platform for developing CLX driven page migration solution. The platform is M5. M5 consists of two key components, hot page tracker and the hot word tracker, and the M5 manager. The hot page tracker and hot word tracker effectively tracks the top K hot pages and hot words respectively, and the M5 manager provides users with the software interface for the synergetic use of hot page tracker and hot word tracker.
Let's start with a quick overview of CPU-driven page migration. In CXL-based memory systems, we have two types of memory, slow CXL memory and fast DRAM. The main idea is to detect frequently accessed pages in slow memory and move them to DRAM to boost performance. To do this, CPUs mainly use three methods, causing hinting page faults, scanning page table entries, and sampling access memory addresses. Let's look at how each of these work. Solution 1 is hinting page faults. In this method, the OS periodically picks a group of pages in slow memory and clears their present bit. That temporarily unmaps them. So when a process accesses them again, a soft page fault occurs. The OS then marks that page as hot and migrates it to DRAM. This approach can find active pages accurately, but it has major drawbacks. Frequent page faults, TLB shootdowns lead to CPU overhead. This overhead hurts latency sensitive apps like Redis. A well known example of this is transparent page placement, TPP. The second solution is scanning PTEs. The second method periodically scans all valid page table entries for slow memory pages. If a PTE's access bit is set, the OS increases that page's access count and resets the bit. After multiple scans, frequently accessed pages are marked as hot. It's simple and uses existing hardware support, but it's costly for large system. Scanning all PTEs take time and access bit only tells whether a page was accessed or not how many times it was accessed, leading to wrong assumptions. A system using this idea is AutoNuma in Linux. The third solution is sampling accessed memory addresses. The third solution uses hardware support like Intel's PEBS. When a cache miss occurs, PEBS can record the missed address in a buffer. When the buffer fills, a interrupt triggers the OS to process these samples and find which pages are accessed most often. This approach doesn't track every access but provides a good approximation with less CPU overhead. It's scalable and efficient, though slightly less precise. The limitation is that current PEBS can't sample CXL memory yet.
Now let's try to understand what is this CXL memory and how the CXL memory controller is being utilized. Our computer architecture can be visualized into the CPU, north bridge, south bridge, and all the peripherals connected to the CPU via either the north bridge or the south bridge. The slower memory peripherals are connected via the south bridge, while the faster peripherals are connected to via the north bridge. The PCI Express ports are connected to the CPU via the north bridge. Now, the CXL memory ports are interconvertible, and the CXL devices can be connected to my CPU using those same PCI Express ports via the north bridge. This is because the CXL.io protocol, which is specified in the CXL.1.0 specification, is actually based upon the same PCI Express 5.0 specifications. So, the same PCI ports can be used to connect either the PCI devices or the CXL devices. Next, looking at the CXL memory, our processor or CPU can now be converted to the CXL devices via the PCI Express ports, and it connects to our processor via the north bridge. All the memory expanders or accelerators, smart NICs, or the SSD cards, all those are connected as CXL devices to our processor via the CXL, via the PCI Express ports. Looking at the type devices which are specified by the CXL specifications, there are three types of devices. All the three types of devices have something common, which is the CXL.io protocol. The CXL specification has specified three protocols, namely the CXL.io, CXL.cache, and CXL.mem. All the three type devices have the CXL.io protocol, which under the hood is based on the PCI Express 5.0 protocols only. That's why it is used for the initialization and the real data transfer. The type 1 devices in addition has a CXL.cache protocol, which enables the devices to have their caches of its own. So now my device can cache the host memory via this CXL.cache protocol as well. The next type of device, in addition to CXL.cache, has a protocol CXL.mem, which enables my device to have a memory of its own. And this memory can now be cached coherently via the CPUs or via my host's caches as well. Moving on to the Type 3 devices, they can be now seen as complete memory expanders because those devices only have a CXL.mem protocol and there are memories which are connected to my device. So my host CPU can see those memory as an extra memory instead of my RAM, which are connected coherently to my host caches. Moving ahead to the CXL controller architecture, this can be seen as sitting in between my host's integrated memory controller or IMC and my CXL DRAM. So this is basically the entire brain of my CXL devices, which implements all the three protocols, the IO, the cache, and the MEM protocols, and it snoops all the data and the addresses which are coming in between my IMC and the CXL DRAM. Taking a greater look at the CXL controller, it can be converted into three broad layers. The first layer being the physical layer of my CXL controller. This implements the CXL.io protocol, which is inherently based upon the PCI Express 5.0 protocols. Next, the CXL.ip protocol stack implements the link layer and the transaction layer of my CXL architecture. The CXL.cache in itself has one or two DCOH engines, which is device coherence engines. This includes device caches and it is used to service all the D2H and S2D requests which come. So whether a request is coming from device to host from our coherent request AFU or whether the request is host to device from our CPU, this DCOH will service all those requests. The next layer implements are near memory hardware functions inside this user-defined AFU or accelerated function unit. You can define your hardware function inside this, which snoops all the addresses which come from our memory to our device or vice versa. It snoops them and implements its own functions with the help of coherent request AFU as well. Next, we'll try to implement our PAC and WAC inside this user-defined AFU and we'll implement those functions here.
Hello everyone. Before delving into CXL-driven page and word access counting, first let's go through a few limitations of the current system. It has been challenging to precisely determine the number of accesses to every page and word with the help of the current commodity systems. For example, Intel PEBS can sample only 1 out of 100 addresses at most. However, as of now, the emergence of a commodity FPGA-based CXL device has opened up an unprecedented opportunity to tackle such challenges. In this discussion, we first describe page and word access counting functions in the CXL controller of such a device. We will be using PAC and WAC as abbreviations in the discussion henceforth. PAC and WAC exploit the inherent capability of near memory processing in a CXL controller to precisely count the number of accesses to every page and word in CXL memory. We will be discussing this entire procedure in broadly three aspects. First, the hardware aspect, then the software aspect, and then how scalable this entire approach is. First, let's discuss hardware. Before discussing the actual hardware, we would like to put out a few assumptions that we are going to make. As in case of most of the x86 systems, we would be using a 48-bit physical address space. Next, a 4 KB page granularity will be used, except when we are specifically allocating 2 MB or 1 GB huge pages. Then, DRAM is accessed with physical address bits 6 to 47 because the access granularity of DRAM is 64 bytes, which is precisely the size of our cache line. That is the third assumption. As we have discussed, 4 KB is the page granularity that we are going to use most frequently or most often. 4 KB accounts to 2 to the 12 bytes. So we will be requiring 12 bits to address into every page. This means that page frame numbers will be determined by the bit number 12 to 47 of our physical address. Now let's go into the hardware. The hardware consists of three key components in case of PAC. Firstly, as you can see in the slide, we have an address to PFN converter. The address to PFN converter snoops every memory access address from CXL IP to the memory controller and right shifts it by 6 bits to obtain the page frame number. Actually, here the physical address that has been mentioned is the bit number 6 to 47 of the actual physical address. This sprucing of the physical address is done by the CXL IP. Then the address to PFN converter right shifts it by 6 bits more to the right to get bit number 12 to 47. That is the page frame number. Next, we have the SRAM unit, which provides a capacity of 4 MB with each entry storing an L-bit access count for a 4 KB page. This SRAM unit consists of tables which are indexed by the page frame number. And thirdly, we have a miscellaneous logic block which consists of an L-bit adder, a controller, and configuration or control registers. Next, if we consider WAC hardware, it consists of almost the same components as PAC hardware except the absence of an address to PFN converter. This is because here in the SRAM unit, we would be indexing it with the help of words rather than page frame numbers. So this entire process or the entire hardware specifically is fundamentally different from event sampling based approaches such as PEBS, since here we are tracking every DRAM access separately. Now a little heads up on what's an event sampling approach. What happens in an event sampling approach is that instead of counting all events, the hardware only samples some occurrences of the event. This helps us in getting a statistical representation of the entire process. This thing actually provides less overhead, and that's why it is being used in most of the systems as of now. Now, how this entire system works together. This is where the work of the controller is there. For a given page frame number, the controller gets the corresponding access count from the SRAM unit, increments it via the help of the adder present inside miscellaneous logic block, and stores it back into the SRAM unit. A similar thing can be seen in the case of the WAC hardware also. One problem that we might face here is in the case of an overflow if L is small. Generally, in most of the practical use cases, this overflow is not seen because 16-bit access counts saturate in about 20 seconds. However, even in the case of an overflow, which is quite unfortunate, PAC may reset saturated counters by accumulating them inside an access count table, which is allocated in the host or device memory. This is done by using D2H, that is device to host, or D2D, that is device to memory, device memory accesses. This is the entire architecture. We have discussed almost the entire architecture. One more thing here is that the SRAM unit is exposed to host CPU as an MMIO region, allowing PAC software to directly access the access counts. Now let's discuss the software aspect of the process. The first thing that software does is that the software interface for PAC and WAC first maps the SRAM unit and registers to an MMIO region. The entire hardware that we discussed in the previous subsection is actually located on a small FPGA, which is an external device that is connected via a wire or maybe a cable or maybe some USB to our system, that is our PC. MMIO is a mechanism that lets software treat device register or memory as if they were normal memory addresses. So, mapping it to an MMIO region actually helps the CPU to address these hardware things via normal load store operations or load store instructions. This helps us to access the access counts through MMIO interface via CXL.io. Now there are some limitations that can be faced in the software. The major limitation is the size of an MMIO region. The size of an MMIO region is only 2 MB. We divide it into two parts, 1 MB to access the access counts in SRAM unit and 1 MB to access the configuration and control registers. However, as we had discussed earlier, the SRAM unit provides 4 MB size. So how do we do it? To access 4 MB of the access counts with a 1 MB region, we designed PAC and WAC hardware functions to use a configuration register to store base address for each 1 MB region that we are accessing currently via this 1 MB region of the access count. So whenever we demand to know an address, we will be getting the base address from the base address register that is present in this 1 MB region. Then we'll be provided with an offset via the PAC WAC software interface. Then we'll be able to access the access count table present in the SRAM by base plus offset. So this is the entire software working or software functioning of our process. Next, let's jump into scalability. Scalability issues arise when SRAM unit is not large enough to store all access counts for a given DRAM capacity. There are broadly two ways in which this can be handled. This is the first way. We'll be using SRAM unit as a cache to store a subset of counters. When cache miss occurs, the controller chooses to evict and write down the access counts to the access count table which is present in the host or the device via D2H or D2D. Next, we reset the counter inside our SRAM because we're using SRAM as a cache and store 1 in the counter. The second way is called limited region monitoring. Here, what we do is that we limit the size of the CXL memory region that PAC or WAC monitors at a time by setting configuration registers that specify the current memory address range, or most specifically, the base address of the current region that we are responding to or that we are seeing with the help of CXL memory. Then we monitor either all CXL memory regions over multiple intervals during a single run, or only one memory region during a single run and repeat it for different CXL memory regions for multiple runs. These are the two monitoring modes which can be called sub-modes inside this limited region monitoring. Practically, WAC hardware supports 120 MB region mapping as of now.
Now let's discuss the usefulness and cost of CPU-driven page migration solutions. Page migration helps move frequently accessed pages from slow memory like CXL to fast memory for better performance. Here the CPU is responsible for detecting those hot pages. To evaluate how accurately and efficiently these solutions identify hot pages, we use two profiling tools. PAC, the page access counter, which records the true number of accesses to each page, and WAC, the word access counter, which measures how many unique 64-byte words within a page are accessed. The test programs are ANB and Daemon. ANB, which detects hot pages by monitoring accessed bits and handling soft page faults. Daemon, which does it by sampling and scanning page table entries. We will initialize these methods across three aspects: usefulness, access sparsity, and performance cost. Access count. First, we check how precisely ANB and Daemon can identify truly hot pages. Using PAC, we compare the access counts of pages that ANB or Daemon marked as hot with the access counts of the actual top K hottest pages. The ratio of these two tell how accurate the detection is. A higher ratio means better identification, while a lower ratio means warm pages are being mistaken as hot. As shown in the graph, most benchmarks have ratios below 0.4, indicating poor precision. Daemon performs slightly better than ANB, but both still misidentify many warm pages. So our first observation is that CPU-driven solutions often identify warm pages as hot pages. Next, we'll look at the access sparsity of these hot pages. Even if a page is marked as hot, it doesn't mean all the data within that page is heavily used. WAC helps us measure how many unique 64-byte words in each page are actually accessed. In some applications like Redis and Memcached, we see that most hot pages are sparse, meaning only a small fraction of words are frequently accessed. Migrating such sparse pages waste fast memory capacity and even pollute CPU caches. Thus, our second observation is that many real-world applications exhibit sparse access patterns, making full page migrations inefficient. Finally, we evaluate the performance over cost of detecting hot pages. Both ANB and Daemon perform costly operations like scanning PTEs, invalidating TLBs, and handling page faults. These operations increase CPU cycles consumed by the kernel and interfere with normal application execution. From the table, ANB increases CPU usage by up to 487% and daemon by up to 733%. This leads to higher latency. So our third observation is that the overhead of identifying hot pages is significant and can easily offset the performance benefits. To summarize, CPU-driven migration solution often struggle to identify truly hot pages. Many of those pages are sparsely accessed and the detection process itself incurs heavy CPU overhead.
Now let's move to our next section, M5, track, filter and migrate. M5 consists of two key components, hot page tracker, hot word tracker and the M5 manager. Earlier, we have discussed about the page access counters and the word access counters. These are a great offline profiling solutions but not good online profiling solutions because on every query they have to get the access counts of all the memory addresses and sort them in ascending order to get the top k memory addresses, to get the access of the top k memory addresses. So this consumes a lot of CPU cycles and degrades performance. So to counter this, we propose hot page tracker and hot word tracker. To make hot page tracker and hot word tracker useful and practical, we determine the following requirements. First, they should be able to handle each memory access every 2.5 nanoseconds. Second, when the host CPU queries the top k hot addresses, it should be able to return them quickly. Lastly, the hardware cost should be reasonable, although it is a secondary constraint. Now coming to the architecture side. Both these trackers have essentially the same architecture. They have two key components, a SRAM based CM sketch unit and a top K sorted content addressable memory unit. This CAM unit stores the top K sorted addresses. Now let's move on to the working. So we have H hash functions. These hash functions can output a value between 1 to W. So given a memory address, it is passed to all the H hash functions and we collect the H outputs. These H outputs are indexed in a H cross W matrix and the values at the particular indexes are incremented by 1 and these incremented values are then passed to the comparator tree to get the minimum value. This minimum value becomes the access count of our memory address. So this memory address comma access count pair is passed to the CAM unit. If there is an address hit in the CAM unit, the access count value is updated in the CAM unit. Else, this access count is compared with the minimum value in the CAM unit, and if this access count is larger than the minimum value, this memory address comma access count pair is put in the CAM unit, and hence we get the top k sorted access counts in the CAM unit, which can be retrieved quickly on a query by the host CPU. Now we will move to the M5 manager. Now let's move on to the second component of M5, the M5 manager. M5 manager has four key components: monitor, nominator, elector and promoter. We have till now identified hot pages and hot words by the hot page tracker and the hot word tracker, but blindly migrating these identified hot pages is not advised because there is a possibility that the pages existing in the DDR DRAM are hotter than the pages in CXL DRAM, and if we migrate the pages in the CXL DRAM to DDR DRAM, it will degrade the performance. So here comes the role of monitor. Monitor collects the statistics of the tiered memory system to identify that whether migrating hot pages to DDR DRAM is useful or not. To do this, it uses three functions: NR pages, which is the number of pages allocated to the node; BW node, consumed real bandwidth of node; BW density, bandwidth per allocated capacity. So by collecting statistics from these three functions, monitor help us to determine whether we have to migrate pages to DDR DRAM or not. There are two guidelines in monitor. If bandwidth density of CXL is higher than bandwidth density of DDR, hot pages should be migrated from CXL DRAM to DDR DRAM as soon and aggressively as possible. Guideline 2. Hot pages can continue to be migrated to DDR DRAM as long as bandwidth of DDR keeps increasing even if bandwidth density DDR exceeds bandwidth density of CXL. Now let's move on to nominator. Nominator has two key data structures, the HPA and the HWA. These two data structures are constantly updated from the hot word tracker and the hot page tracker. The HPA has an entry corresponding to physical frame number of every identified hot page, and corresponding to every entry there is a 64-bit mask where the ith bit is set to 1 if the ith word in the hot page is identified as a hot word. There are two types of nominator, the hot page driven nominator and the hot word driven nominator. In the hot page driven nominator, the HPA is first filled from the hot page tracker and the 64-bit mask is set to 0. Next for every word in the HWA which is filled from the hot word tracker, we get the physical frame number of the page in which the word exists and the word is present, and set the corresponding bit in the 64-bit mask of that entry in the HPA as 1. So by doing this for all the words in the HWA, we can identify dense pages. We can identify true hot dense pages, and that will be nominated by the nominator for migration. Second type of nominator is the hot word driven nominator. In this, initially the HPA data structure is empty and it is filled by the HWA data structure. For every word in the HWA data structure, the physical frame number is calculated and the entry in the HPA is filled, and the 64-bit mask is incremented at that bit. So after doing this for every word in the HWA, the true hot dense pages are identified and are nominated by the nominator. There are two guidelines for the nominator. Hot page tracker driven nominator can be useful for applications with the mix of dense and sparse hot pages such as rooms and liblinear. Hot word tracker driven nominator can be useful for applications with only sparse hot pages such as Redis and CacheLib. Next, we move on to elector.
Next, moving on to our third stage, which is our elector. Its main task is to control the frequency of page migration and the rate control and the migration controls. Its main task is to snoop whether our page migration solutions are actually increasing our bandwidth or not. If it is, it will just migrate those pages, otherwise it will stop for a few units of time. In the algorithm, you might see that there is a default frequency of our page migration, which is needed to be scaled by this ratio proportional to the bandwidth density of our CXL memory and our DDR memory. This is the time which is calculated for which the selector will sleep in order to control the rate. We'll calculate the total bandwidth of our DDR DRAM and our CXL DRAM and the relative bandwidth density of our DDR DRAM. Now, if that relative density which we calculated right now is greater than the previously calculated one, means we are actually benefiting from the page migration solutions we derived right now. So, we'll promote the addresses or the pages which were actually nominated by the nominator. Once this promotion is done, we'll make ourselves ready for our next iteration. So our previous bandwidth total will now become the current bandwidth total, and our previous relative bandwidth density of the DDR DRAM will become our current relative density. After this, we'll sleep for the t times t units of time, which was calculated using scaling of our default frequency. With this, we have elected the ones which needs to be migrated. Then comes our promoter, which actually promotes and migrates those pages. Promoter's main task is to update those proc file pages in our Linux kernels, which actually includes the addresses or the pages which needs to be migrated and whose page table mappings have to be remapped. This then does the migration of pages from our CXL DRAM to our DDR DRAM. With this, we are done with the specification of M5 and will move ahead with the evaluation and the discussions.
To evaluate our design, we use a dual socket Intel Xeon setup with DDR5 memory. We compare three page migration solutions A and B, Daemon, and our proposed M5. ANB and Daemon run on different Linux kernel versions, while M5 is built on a newer kernel. We intentionally did not port the older solution to the latest kernel to maintain fairness and stability during evaluation. For benchmarks, we selected a wide range of memory intensive workloads, including Libneo, Redis, and multiple graph based applications. Each benchmark was sized to create a substantial memory footprint, and we limited the usable DDR capacity to allow roughly half of the pages to migrate, ensuring meaningful migration behavior during testing. A key challenge in page migration is detecting hot pages both quickly and efficiently. We compare two tracker designs, CM Sketch Tracker and Space Saving Tracker. In CM Sketch, SRAM is used to store access counts, while CAM keeps only the top entries, making the design compact and scalable. The space saving tracker, on the other hand, maintains a sorted structure that tracks every address and its access count. This provides higher precision but at the cost of significantly larger area and power consumption. The key takeaway here is that CM Sketch separates the counting and ranking processes, allowing it to scale much better under strict timing and hardware constraints. Next, we compare both designs in terms of size, power, and accuracy. The space saving tracker requires much more area and power, while CM Sketch achieves similar accuracy using far fewer hardware resources. It also supports a larger number of tracking entries, which further enhances its practical accuracy and efficiency. Here we compare hot page detection accuracy across CPU based Daemon and our M5 approaches. M5 with CM Sketch consistently delivers higher accuracy than both space saving and CPU driven methods. It effectively identifies not only the global hot pages but also the near hot ones, ensuring better migration decisions and improved memory performance overall. Finally, we'll look at the overall performance of all three systems. ANB provides only a minor improvement while Daemon struggles due to its long scanning intervals, leading to slower response times. M5, in contrast, outperforms both by detecting hotter pages earlier and migrating them more efficiently. Workloads like Redis and libnear benefit particularly well from M5 given their memory access patterns. Overall, M5 delivers higher performance with lower overhead, demonstrating effectiveness as a fast and efficient page migration framework.
Now let's talk about the scalability of the Top-K tracker based on CM Sketch. As CXL memory and application footprints grow, the number of unique memory addresses also increases. This can lead to more collisions in the CM Sketch entries, since each entry estimates how frequently a specific address is accessed, and that reduces accuracy. The figure shown in this slide shows how accuracy changes when we keep only 32K CM Sketch entries while increasing the memory usage. This has been tested using multiple instances of benchmarks like MCF, ROMS, Photonic, Cactus PSSM, up to 32 processors, which used around 20 to 27 GB of memory. The graph shows that accuracy decreases, but only gradually, which means that the top K tracker scales gracefully. Considering the overhead of the tracker, the top K tracker with 32K entries that we have used here takes just 0.01% of total chip area of an 8 GB DRAM module. So it is very lightweight. For larger memories, we can simply increase the entries from 32K to 128K, or we can use multiple trackers like 32K entries for each tracker and one tracker per DRAM rank or module without much overhead. Finally, the case of reading huge pages. As we have discussed perhaps in section 3, we will be allocating mostly 4 KB pages. However, we can also allocate large pages or huge pages such as 2 MB or 1 GB page granularity. If an application allocates 2 MB huge pages, M5 can easily extend its tracking. There can be two ways by which it does so. One way is that we can aggregate 4 KB hot pages, or the second way is by using a separate tracker with 2 MB page granularity.
Now coming to related works. So this paper identifies two related works. First is the Intel flat memory mode. In this, when a CXL memory address is accessed, the memory controller swaps a 64-byte word at the CXL memory address with a 64-byte word at the one-to-one mapped DDR memory address. However, IFMM is limited to the case where local DDR memory and remote CXL memory have the same capacity because of one-to-one mapping between CXL and DDR memory address for swapping. So this can be synergetically used with M5, where the words in sparse pages can be migrated by IFMM and the dense hot pages can be migrated by M5. Second, the second related work is NeoMem. Here, tracking hot pages in the CXL controller as congruent work. So this also tells about a top K tracker, but however, in contrast to NeoMem, we also present page access counter and word access counter, which have enabled us to precisely evaluate the access count ratio. Lastly, NeoMem does not track hot word addresses while M5 does. Following this, coming to conclusion. First, this work proposed a CXL driven hardware assisted profiling solution that leverages the unique capabilities of a FPGA based CXL device. Second, this work showed that CPU driven page migration solutions often not only classify warm pages as hot pages, many of which may also be sparse but also incur notable performance overhead. Lastly, this work presented M5, a platform for developing CXL driven page migration solutions. So, thank you.